Hey, hi everyone. So welcome again to another video of Math 030. So for this video and the succeeding videos, I will discuss the arc length and the curvature. So if you have a given vector valid function, uh, that is this blue curve, you can approximate now first the length of this curve. No? You can imagine straight lines connecting these points that could approximate the length of this curve. No? But in calculus, you can make things easier by utilizing the infinitesimals, no? So let's say, for example, we have a two-dimension or a two-dimensional curve in y and x only. And let's say we have this curve, for example. Say this is the curve. Yeah. So we can imagine, let's say we have 2 points here, and this line connecting these 2 points, let's call this the ds, or we can call this dl now for now. This is the infinitesimal length. No? You can imagine if you zoom in a little bit closer to the curve, it will be approximately a line. Now for this line here, or this line segment, we can form a triangle, no? As you can imagine here, a right triangle that has a dimension that is also an infinitesimal. We have the dx and the dy. Now, if we use the Pythagorean theorem, we can create a relationship between these three infinitesimal variables. We have dl squared is equal to dx squared plus dy squared. Okay. Now, we know that these variables, or specifically the y coordinate and the x coordinate, can depend on a parameter, no? Which is called the t. No? Usually we utilize t as a parameter for describing the coordinates of x and y. Therefore, what we can do here is we can divide this by dt squared for both sides. Okay? So that we can introduce another variable, no? or basically another parameter. Now, what we can do here is simplify this, and then we can actually I think it's better to just multiply this by dt squared over dt squared, no? So distributing this, no? And then finding the square root, we have dl, no? So finding the square root of this as well. So we have dl is equal to the square root of, we have dx squared over dt squared, right? Plus dy squared over dt squared. Now, if you find the square root of dt squared, this will be just dt, right? So this will be just multiplied by dt. And in doing so, now we have this relationship of dl versus the derivative of x with respect to t, no? For each of the coordinates of x and y. Now, if we want to find the sum of the lengths, no? So basically in calculus, integration means the sum, no? So if you find the sum of all these lengths, you can imagine this curve, we have these lengths here. If you sum this infinitesimally from, let's say, from A to B, no? Sorry, from A to B. So when t is equal to A and when t is equal to B. Therefore, you want to integrate this from A to B. Yeah. So this will cancel out now. So the integral and the derivative sign will be just L. And then simplifying this, actually you cannot simplify this anymore. So this will be the length of your curve will be the definite integral from A to B of the square root of, we have dx over dt. So we can just factor out the square, no? Plus we have dy over dt and then squared. And then multiplied by dt. So basically this is the arc length, no? The length of this curve at 2 dimensions only. 2-dimension curve. Now, for 3-dimensional curves or a curve in space, this will be just this, no? So we can just add another term for the sorry the third axis. No, actually this should have a dt. And after that, this will be simplified into if this looks familiar, no? So this looks actually familiar. This is actually equal to what, no? So this is the length of your first derivative of your r, right? So if this is your x and y and z coordinate, you find the first derivative, and then you find the square root of their sum of their squares, then this will be just the length of your first derivative of your vector valued function. Therefore, we can describe the length as a definite integral from a to b of the length of r prime of t and then multiplied by dt. Okay, so this will basically be your second formula. No? Yeah. Okay, so what's next here? So we have an example, no? So we want to find the length of the arc of this circular helix with this given vector equation. So from point 100 to point 1025. Okay, so we started from this and then we have this direction, rotating, no? And twisting from 100 to 1025. Now, how do we find the arc length? No? So the length of the arc is equal to the definite integral from a to b of the absolute value of r prime of t, or not absolute value, but length, no, of r prime of t. So we want to first find the first derivative of r. So the first derivative of r will be equal to, so finding the derivative of this, we have negative cosine, negative sine, t and then I hat, and then, actually this should be a vector, no? So plus we have cosine t j hat, and then plus, so the derivative of t is k, so we have only k. All right, so what's next? So we want to find the length of this vector, and actually we have also the given t, right? Do we? Okay, the t. T is not given, no, but I can actually find the length anyways also. So let's worry about the t later. So to find the length of your vector valued function, the first derivative of your vector valued function, then this will be just the square root of the sum of the squares. So we have negative sine t squared plus we have cosine t squared, and then plus we have 1 squared. Okay? So if we simplify this, we have the square root of sine squared t plus cosine squared t plus 1. And does this look familiar? So this is actually equal to 1. So this is equal to 1. We have the square root of 1 plus 1. So therefore, the final answer for this is the square root of 2. Okay. So we already have this answer. Now, how do we utilize this? So we can just substitute the value square root of 2, okay, to our formula, to our definition. So therefore, the length is equal to the definite integral from a to b of the square root of 2 dt. Now, we have to worry about this a and b. So the a and b is what? No? So based on this curve, we have a given initial point and the final point in this curve. And if we can observe this, no? As we can see, we have 1, 0, 0. So what value of t will make this 1? What value of t will make the 0? What value of t will make the 0? So you can imagine for the first, actually for the z coordinate, we know that t is equal to 0 already. And if you substitute t is equal to 0 here, so we have 0 again. And if you substitute 0 here, then you have 1. So cosine 0 is 1. So therefore, your a here is actually equal to 0. Okay? And then for the final point, if you observe for this, so actually here, no, you can already see that the t here is 2 pi, right? So t here is 2 pi. And if you substitute 2 pi here, so sine 2 pi is equal to 0. And then cosine 2 pi is actually equal to 1. So this will be equal to 2 pi. Therefore, the length here, finding the derivative of this. So what is the derivative of square root of 2 dt? So this will be just square root of 2 times t only, no? And then evaluated from 0 to 2 pi. Therefore, if we simplify this, what do we have? No? So we have square root of 2 times 2 pi, okay? And then minus square root of 2 times 0, right? So simplifying this, we have 2 square root of 2 times pi as our arc length. So this will be your final answer. So the length of this curve from here to here, if you measure this as a string, no, you can imagine a string that extends this curve. The length of that string will be the square root, 2 times square root of 2 times pi. Okay, so now we already have the arc length, no, the definition of the arc length. Let's now describe the arc length function. Now, if you have a vector valued function, this black curve here, then we can describe the arc length depending on the variable or the parameter t. So if the parameter t is, let's say, 0, then usually you start with 0, no? And you have no arc length. But if you have a value of t here, let's say 2, then you will have an arc length, no? If let's say t is equal to 5, so let's say this is the distance from this t is equal to 0 and t is equal to 5, for example, then you have a length or an arc length function that represents this vector. No? So you can describe your vector valued function as a function of its arc length. So what can we do here? No? So what can we do here is that instead of defining your arc length as just L, we can vary, no, this L as a function of the parameter t. So the arc length, which is also this, no, this is the arc length function, okay, is equal to the definite integral from e to t of the length of r prime of u du. Okay? And what we will utilize here most of the time is just this, no? So just remember this one, and this will cover most of what we need, no? So let's say we have this given, we have the same given example from last time, and we want to find or we want to reparameterize, no? This helix curve with respect to the arc length. So what does that mean? So instead of this vector, okay, instead of this vector as is a function of this t, we can transform or we can reparameterize. Okay, we can reparameterize by having its independent variable as a function of its arc length. Ano? So what should we do here, or how do we do this? So in doing so, what we need is the definition again, no, which is ds over dt is equal to the length of r prime of t. So only you need to memorize this one. So did we already solve this one? We already solved for this one, right? So from the previous example, we already solved for that, which is, where is it? This, okay? So we have this already. This is a given or the similar given from the last slide. So we already have a solution, no? So we can make the discussion a little bit faster. So this is equal to the square root of 2. Now to find the s function, we want to find the integral, di ba? So we can cross multiply this to the other side. So we have ds is equal to square root of 2 dt, and then integrating this both sides, okay? From what? No, so from 0, no? So when t is equal to 0 up to t. So we have 0 to t here. So therefore, we can cancel this out. So we only have s here is equal to the definite integral from 0 to t of the square root of 2 times dt. So evaluating this, no? Evaluating this integral, what do we have? Okay. So actually, this might be confusing. Now we can change the variable to u for now. Well, just for now, no? So this will become the integral of square root of 2 du. We already solved for this, no? So this will be square root of 2 times u, evaluated from 0 to t. So how do you evaluate this definite integral? We can substitute t here. So we have square root of 2 times t minus square root of 2 times 0. So we can cancel out as 0. So the s here, or s as a function of t, will be equal to square root of 2 times t, which is 2 times square root of 2 times t. So therefore, to solve for this, no, or to have a relationship between this, no, to parameterize our vector value function into this as a function of its arc length, we can now substitute the t here given this. So we can write this as t is equal to s over the square root of 2, right? So therefore, what we can do is the vector value function r is equal to cosine s over square root of 2 and I hat. So this will be s, sorry, no? And then plus sine s over the square root of 2 and then j, and then plus, so t here is also s over square root of 2 times k. Okay, so this will be your vector value function in terms of s now. So this will be your final answer. So if you want to find, let's say, the coordinate of the coordinate of your curve, given the length, no, of your curve that you want to figure out. No? So let's say you have this curve, you have a given length, no, that is, let's say the length here is s. You can find the coordinate here that is your vector valued function at s. So we have here your x, y, and z coordinates. Okay. So moving on, we have also the curvature to describe our vector valued function. And what is basically a curvature? No. So the curvature from the name itself, it just describes how curved a given vector is at any given point. So you can imagine, let's say this is our arbitrary vector value function. Then, as you can see, if this is your curvature, sorry, at this point, no, you have a curvature that is very small since it is not much, no, it doesn't deviate much from a straight line. So this has a small curvature. But comparing this to this point, so let's say this point, the curvature of this will be much greater since it has a larger deviation from a straight line. So you can imagine how much does it deviate, or how much does the curve deviate from a straight line, no? So the ratio of that, which is also the curvature, is the ratio of your tangent line over your straight line that is also the arc length. So this ratio is now called the curvature. No? And the curvature varies, no, depending on the position of your curve. So the curvature is a function of your parametric variable t. So to solve for this, you have to find the derivative of your tangent vector and the derivative of your r vector. Okay? And also including their lengths, no? So let's say, for example, we have this given. So show that the curvature of a circle of radius a is 1 over 8. Okay, so again, what is the curvature of a circle of given radius a? We have 1 over 8. Okay, so what is now the parametric equation of a circle? So a circle has a parametric equation. Now we have r of t. We have cosine t I hat. Okay, plus we have sine t j hat. Yeah. So this is the parametric curve or the vector value function of a circle at z is equal to 0, basically. So to find the curvature, which is your kappa, so kappa is the curvature, we have to find the unit tangent vector over the first derivative of your vector value function, and of course the length of this derivatives. So let's find first the first derivative of this. So we have r prime of t. So we have negative sine t I hat, and then minus, sorry, not minus, but plus cosine t j hat. Okay, so what's next? So we want to find the length, no? So for finding the length of your first derivative of your vector value function, you just want to find the square root of the sum of the squares. So we have negative sine t and then squared and then plus cosine t squared of each of the coordinates. So this will become the square root of sine squared t plus cosine squared t. So what is this? So using the trigonometric identity, this is actually equal to 1. So if this is the square root of 1, then this is equal to 1. So the length of your vector valued function is equal to 1. So this basically means that your the length, no, of your vector valued function is constant. Oh, sorry, the length of its first derivative is constant. Okay? And after that, we want to find the tangent vector. So what is the definition of a tangent vector or a unit tangent vector? So the unit tangent vector first is equal to r prime of t over the length of your r prime of t. So we already described this. No? So this is your r prime of t. So we have negative sine t I hat plus cosine t j hat. Ayan. And then over the length, so we have 1. Okay, sorry, we have a length nga pala, no? So the radius here is A. Sorry, I forgot to mention the A, no? So the A here it should be here. Based on the form nga pala, I forgot, no? So the form here is you have A, sorry, you have x minus h is equal to r cosine t, right? For x, and then we have y minus k is equal to r sine t. So basically your our radius r is A, so there should be an A here. Sorry, I forgot that one. So we have negative A here and then positive A here. So this will be negative A sine theta and then we have A cos square theta. So let's remove this again. So we have the square root of A squared sine squared t plus we have A squared cos squared t. Therefore, if we simplify this, we actually can factor out this A squared. So we have the square root of A squared and then sine squared t plus we have cosine squared t. Yan. So we can simplify this actually no into the square root of each of these two terms. Actually not terms no, but each of its factors. So we have the square root of a squared is equal to a, so this will be a. And then we know that the square root of this is equal to 1. So we have multiplied this by square root of 1, which is just 1. So therefore your r prime of t is equal to a. So we can write this one, sorry, no. We can write this one as this. Yeah. So divide this by the length of your r prime of t, which is this, which is a. So therefore, dividing this both by a, we can cancel this a here. You have your tangent vector that is equal to negative sine t I hat plus cosine t j hat. So now to find the length, sorry, the first derivative first now. The first derivative of your unit tangent vector. So we have here negative cosine t I hat plus we have this will become negative, right? So negative sine t j hat. Ayan. Okay. So to find the length of your unit tangent vector, that is the first derivative of pala, no? We want to find the square root of the sum of the squares. So we have the square root of negative cosine t squared plus we have negative sine t squared. So if you simplify this, we have another cosine squared plus sine squared t, which is equal to 1. So we have square root of 1, which is equal to 1. Therefore, your the length of your unit tangent vector, actually you can already figure this out that this is a unit tangent vector. It will automatically be, or it will automatically have a length of 1 if it is a unit, no? Unit tangent vector. Okay, this one or this one. So therefore, your kappa here will be equal to 1, which is this, no? And then over A, which is this. So the curvature here is equal to 1 over A. Therefore, it proves that the curvature of a radius circle A is 1 over A. So what does this mean? What is the implication of this? So the larger the radius of your circle, so larger A is lower curvature, but for smaller a, higher curvature. So what does that mean? So you can imagine two circles, one small circle and then one big circle. So this smaller circle has a higher, what do you call this, no? You can see here a higher deviation from a straight line than this circle. So basically, if your circle is very big, no, you can imagine a very big circle, like the Earth, no, you can imagine Earth as a circle, no. The distance between 2 points is approximately a line, no. So the curvature is closer to zero. So that's basically what I mean. If you have a tennis ball, the curvature, you can feel already that it is curved, no? Compared to the Earth, if it is very big, no, then the distance between 2 points, you can imagine between two persons, will be approximately a straight line. So therefore, the curvature is much smaller for bigger circles. Okay, so this with this given curvature can also be found instead of a function of its unit tangent vector and its vector valued function. It can be simplified to just finding the first derivative and second derivative of your vector valued function and simplifying this definition. Okay, so we won't have a derivation or a proof of this equation, unfortunately, just to save time, no? So we have this given for faster solution, no? Sige, let's try using this formula to solve for this problem. So we want to find the curvature of this twisted cubic. Okay, R is given at the general point and at 0, 0, 0. So what do you mean by at a general point? So this should be a function of t. Okay, and then at 0, 0, 0 is when t is equal to 0. Okay, because when t is equal to 0, as you can see, this will be 0, t is equal to 0, 0, and so on. No? So to find this curvature, what we have as formula, we have your curvature or kappa as a function of t that is equal to the length of your r prime of t cross product of r double prime, no, of t, and then all over r prime of t, its length, and then squared. Sorry, and then cube. Yeah. Okay. Okay. So what do we want to find first is the first derivative and the second derivative. So the first derivative here, so the first derivative of this vector valued function is we have 0. So I'm not putting this vector anymore now at this point. So I will compare this later. So these are all vectors now. So this vector valued function, we have 1, we have 2t, and then plus 3t squared. Sorry, not plus, but comma 3t squared. And then r double prime of t, which is also a vector, that is equal to, so the derivative of 0, sorry, 1 is 0. Derivative of 2t is 2. Derivative of 3t squared is 6. Okay, so what do we have next? Sorry, these should be vectors now. So the next thing we should do is to find the cross product of these two vectors, no? So to find the cross product of r prime of t and r double prime of t, we have to find the determinant of these two vectors. We have I, j and k, and then we have what do you have here? So r prime of t first, no? So we have 1, 2t, and then 3t squared, and then 0, 2, and 60. Okay, so doing the crisscross method now, so I will only look at this. So we have 2t times 60. 2t times 60, this will be 12t squared. And then minus, so sorry, I'm going to visualize this as that. So we have 6t squared, right, for I hat. And then plus, so for j hat, we have this. So multiplied by 0, ano? So this will be just 0. And then for this, we have this. And then upwards to this, we have 60. So minus 60 j hat. Okay, and then plus, what's next? So we have k. So k here, we have this downward, so we have 2. So plus 2. And then this one, we have 0. So minus 0, and then k. Okay, sorry. I'll just simplify this so we have a lot of space here. So the cross product R prime of t and R double prime of t is equal to, so we have 6t squared I hat, and then minus 6t j hat, and then plus 2k. So what's next? We want to find the lengths. So the lengths of your cross product. So to find the length of your cross product, we just want to find the square root of the sum of the squares. That is equal to, we have to square this, or each of the coordinates, no? The vector coordinates. So square this, square, and then minus 6, and then, sorry, not minus, but negative 60. Yeah, negative 60 squared, right? Sorry, squared. And then plus, we have 2 squared. Yeah. Simplifying this, we have the square root of, this will be 36 t to the fourth, and then plus 36 t squared, and then plus 4, right? So we have a common in this 4, so we can factor this as 4, and then we have 12, right? No, 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 no. 9. 90 to the fourth plus 90 squared plus 1. Okay, so we can simplify this further as we have the square root of 4 is 2, so we have 2 times the square root of 9 t to the fourth plus 9t squared plus 1. So this is your length, you know? So this is your length now, no? The length of your cross product. Now to find the length of your r prime of t, so r prime of t, so what is r prime of t? This one. So this will be the square root of 1 squared plus 2t squared, and then plus 3t squared. So simplifying this, we have 1 plus 4t squared. This should be a square here, no? Plus we have 9t to the fourth, right? Okay, is that right? Okay, it's right, no? So we have this as our length. So therefore, your curvature as a function of time. So at a general point, this is equal to, we have 2 square root of, so this one of 2 square root of 9t to the fourth plus 9t squared plus 1. And then all over, we have the square root of 1 plus 4t squared plus 9t to the fourth. And then don't forget the cube, no? So we have still a cube here. So cube. So this will be the general function for the curvature. Ayan, at the general point. So given a value of t, you can find the curvature. Okay. Now, if we want to find the curvature at t is equal to 0, so at k, the kappa of 0, this is equal to, just substituting 0 here, no? So we have 2 square root of, so this will be 0 plus another 0 plus 1, and then all over, we have here the square root of, we have 1 plus 0 plus 0, and then cube, right? So this simplifies into, so the square root of 1 is 1, and then cube the square root of 1, or sorry, the cube 1 is will still be 1. And then what do you have here? So this will be equal to 1. This will be equal to 2 times 1. So this will be 2. So we have here, we have 2, no? As our curvature when t is equal to 0. Yeah. Okay. So that's it. So you can try answering the exercise now. Yeah. Okay, so if you can observe, this has a similar formula for 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 curvature in 2 dimensions, no? So we have this formula of curvature in only 2 dimensions. Although you might not be familiar with this, but we have this formula. This exists. So let's just show that this formula also works. So find the curvature of the parabola at the point 0, 0, and 1, 1. So again, the formula of the curvature, well, for two dimensions, no? So kappa of x is what do you call this? The length of f double prime of x, actually the absolute value only, And then we have 1 plus y prime, and then squared, or sorry, f of x pala to, no? So right, so f of x, I keep forgetting this. Yeah. F prime of x and then squared, and then cube. Okay, right? Sorry, 3 halves. So this is our function, no? So basically your function is f of x is equal to x squared. So therefore, to find the first derivative, so the first derivative will be just 2x, and then the second derivative will be 2. Okay, so substituting this to our formula, the curvature kappa of x is equal to, so we have the length or the absolute value of 2, okay, and then over 1 plus f prime of x squared. So we have 2x and then squared, and then raise this to 3 halves. Yeah. Okay, simplifying this, your kappa will be, or the kappa as a function of x will be 2 over 1 plus 4x squared raised to 3 halves. Okay, so now to solve for your curvature at points 0, 0, and 1, 1. So what is this? So k or kappa or the curvature is a function of x. Therefore, we should use x here. This is y, this is x, this is y. So we have x is equal to 1. So, sorry, 0 first. So kappa of 0 is equal to 2 over, so using this formula, we have 1 plus, so this will be just 0 raised to 3 halves. So therefore, this will be 2. Okay? So the curvature at 0 is 2. And then the curvature at 1, we have 2 over 1 plus 1. Okay? And then 3 halves. So this will be also 2, right? This will still be 2. Is it right? Is that, huh? Really? This will be 2, sorry. Square root of 2 raised to 3. Sorry. So we have 2 over 2 raised to 3 halves. Ayan. So therefore, if we simplify this, actually, we can just subtract here. We have 1 minus 3 halves. So this will be 2 raised to negative 1 half. Or basically just 1 over square root of 2. Or square root of 2 over 2. Which is approximately 0.707. So kappa of 1 is equal to this. Or actually this one. Okay, so what does this mean? What are the implications of this? So if you visualize a parabola, we have this blue curve here as your parabola. So this is your 0, 0, and then you have this point here as your 1, 1. So the curvature at this point, as you can see, no, it is curvy at this point. So how much does it deviate from the straight line? So as you can see, the deviation from a straight line, how much it deviates from a straight line is very high compared to this. As you can see here, this is almost a straight line, no? This is almost a straight line. The deviation of this is almost a straight line. Therefore, the curvature is lower here compared to this one. Curvature is higher. So this is equal to 2, and then this is equal to 0.707. Yeah. Okay, so that's it. Okay, let's move on to the next topic. So yeah, I'll just create another video for this. So see you guys for the next video.